SwayamPrabha. Digital India. Educated India.
Welcome to today's lecture. This is the second lecture on basic control systems for mechanical engineers. In the last lecture, we studied about linear systems and linear time invariant systems, Laplace transform, and finally we came to final value theorem. In this class, we are going to use Laplace transforms to understand control systems. So, the most important representation of any control system is called the transfer function. So, what is a transfer function? A transfer function is ratio of Laplace transform of the output to Laplace transform of the input such that initial conditions are equal to 0. So, mathematically we can represent this as transfer function Gs as the Laplace transform of the output Ys divided by Laplace transform of the input Us. So, this is the transfer function. In short, we call it TF. So, we can express, once we have this transfer function, it can be expressed as Bs by As as we discussed in the last lecture. The roots of B of S are called zeros of the transfer function G, and roots of As are called poles of the transfer function. So, this transfer function is the most standard representation of any system and is quite frequently used, and for the bulk of this course we will be using this transfer function representation. Now, coming to how you would say you want to do this in MATLAB, what we would do is we would define this polynomial B and A. For example, say the polynomial is s square plus 3s plus 2, then we would express it as 1, 3, 2, and A of, say A of s is s cube plus 3s square plus 3s plus 2, then it would be expressed as 1, 3, 3, 2, and then we can, if we want to write down G, we just use the function TF B A to get our transfer function G. So, now we have studied the transfer function mathematically and defined it. So now we'll focus on doing one example. So let us consider a simple spring mass damper system. So here we have the mass m, spring with constant k, and damper with constant b. And let us denote this position as x, the force as F. So if we write, so the first thing we'll do to get the transfer function with F the force as the input and x the displacement as the output. So the first thing we do is we write down the equation of motion. Here for the sake of simplicity, what we are doing, x and f are functions of time, but we are just dropping that notation. Now we can perform the Laplace transform, and as discussed in the last lecture, for x double dot double derivative we will multiply it by s square, for a single derivative multiplied by s. So here for x the Laplace transform is x, and for f Laplace transform is capital F. So based on this we can get ms square plus bs plus k and from this we can get, assuming x is the output and f is the input, so this is a transfer function for this simple system. Now let us consider another example. So here we now consider two masses m1, m2. The position of the first mass is x, the other one is y. This is K2, K1, K3. Similarly, dampers we have B1, B2, B3. And the forces which act on these masses F1, F2. So here we are considering x and y as the outputs and F1 and F2 as the input forces. So we want to find how the transfer function between x and F1, x and F2, similarly y and F1 and y and F2. So first we will write down the equations of motion. So we get m1 x double dot plus b1 x dot plus b2 x minus y plus k1 x plus k2 x minus y is equal to F1. This is for the first mass. The equation of motion for the second mass is m2 x double dot plus b2 y minus y dot minus x dot. Sorry, it should be x dot is y dot here in the first equation. Similarly here we will have b3 y dot plus k2 y minus x plus k3 y is equal to F2. So once we have these equations of motion, we can insert the convert it into the Laplace domain. So what we will have is m1 s square plus b1 s plus b2 s plus k1 plus k2 the whole into x of s. And similarly, we will have minus b2 s minus k2 y of s is equal to f1 of s. Similarly, for the other equation, we can write m2 s square plus b2 s plus b3 s plus k2 plus k3 into y of s. And similarly, we can do b2s minus k2 x of s is equal to f2 of s. So now we can formulate it in terms of matrices x of s, y of s. And this matrix here will have m1 s square plus b1 plus b2 s plus k1 plus k2 minus b2 s minus k2. Similarly, here we will have minus b2 s minus k2, and here we will have m2 s square plus b2 plus b3 s plus k2 plus k3. Once we have this, we can find x of s and y of s. Will basically be inverting this particular matrix. So we'll let us denote this matrix as M. So you'll get M inverse times F1 S F2 S, and based on that we can find our transfer functions x of s divided by f1 of s, x of s f2 of s, y of s by f1 of s, and y of s by f2 of s. So I'll leave that as an exercise for you to try out and complete this problem. So now we have studied about transfer function and how to find transfer function. First, simple for dynamic systems. So we have discussed two examples. Now we'll move on to understanding a concept which is quite common called the DC gain. So DC gain is the ratio of output to input when all transients have decayed and we make the assumption that the input is a step. So it's 1 by s. So what we are going to do here is we are going to apply the final value theorem. So based on this, as we have seen, the limit as t tends to infinity y of t, in the last lecture we saw that final value theorem tells us that this is the limit. Now, as you know from the definition of the transfer function, y of s is equal to g of s to u of s, right? So, based on this, if we substitute this into this equation, you will find that it's basically tends to infinity y of t limit s tends to 0 s g of s u of s, and if we make the assumption here, this particular assumption that u of s is 1 by s, we'll get, sorry for that, we'll have limit g of s divided by 1 of s, these will cancel each other out and we'll get limit s tends to 0 g of s, and this is called the basically the DC gain. So, let us take one example. So, let us take g of s is equal to 4 times s plus 1 divided by s square plus 4s plus 10. So, the first thing you need to check if is this system stable, because as we have seen in the definition of when we discussed final value theorem in the last class, we saw that s of y, the condition for this final value theorem was that s should be stable or basically have poles which are in the left half plane. So, if you draw the s plane, this is the real part, imaginary part, it should be in this half. So, if we look at this, we see that the real part of the roots of s square plus 4s plus 10 will be, the real part of the poles will be less than 0. So, it satisfies this condition. So, then we can insert, we can find the DC gain by setting it to the limit g of s is equal to 4 by 10 is equal to 0.4. So, now we have studied the DC gain. The next concept we will move on is something called the block diagram. So, say we are given this particular block diagram. So, you will find in control systems many times you will be given a block diagram and you will need to simplify it to get a simple expression between your input and output. So, we are going to study different cases for block diagrams. So, first case I will say this is more like a cascaded system where you need to find relationship between y and u, and in this case y of s u of s is basically g1 of s into g2 of s. So, basically when they are put in this configuration, it is basically just the product of the two transfer functions. The next one is, say we are given a u here and transfer function g1, another transfer function g2, and they are summed up to give y. So, this is basically the summation. So, you can write y1 y divided by u is basically g1 of s plus g2 of s. And the third one is basically we have some r here, we have some g1, and this is our output y, and this output is fed back to sorry here is fed back through our transfer function g2, and up this is basically a feedback configuration, and this is basically, since there is a negative sign, we'll call it the negative feedback. So the transfer function between y and r in this case will be g1 divided by 1 plus g1 g2. Next, what we are going to do is we are going to focus on algebra of these block diagrams. So many times you will want, these block diagrams can become quite complicated. So for example, let us consider one case where we have a transfer function g1, and there is a input u1, the output is y1, and say we are considering another input y2. So we want to move this pickoff point from here to here. So this can be equivalently represented as now, since we are moving this point from here to here, we have y here, and we'll take this point here. So we'll need to put another transfer function here, which is 1 by g2. In this way, we can move this pickup from here to here. Now, the most important part is whenever you do this algebra, you always need to understand whether it gives you the same relations. So for example, here what we had in the first one was that y1 by u1 is g1 and y2 is u2. So we get the same relations. So if we look at this first one, we get y1 by u1 is equal to g1, and y2 by this should be u1, y2 by u2, this should be g1, so will be g1 into 1 plus g1, 1 divided by g1 here, so we'll get 1. So if you see, both the relations are same. Another common rule for algebra of block diagrams is we have u1 here, we have u2 here, there is a we do u1 minus u2 and is fed to g1 to get y1. So this can be equivalently represented as, say we want to move this summation from this point to this point, that is after g1. So in that case, what we'll do, we'll take u1 multiplied by g1, similarly u2 again g1, and since we have moved the summation block here, Based on this we can get y. So if you do a similar exercise, you will see that you get, now you still get the same relationships in both the cases. And the third one is, let us consider configuration where we have R, the case of the negative feedback we had seen. So here we have G1, G2, and we have Y. So this can be equivalently represented as, so now say I have this here G2 in the feedback path. I don't want that G2 in the feedback. So I want the feedback to be gained to be just 1. So in that case we'll move this particular G2 here. So basically you will have your summation here plus minus, you will have G1, you will have G2, you have Y, and this is unity gain on the feedback path. Now since we have done that, to compensate for this, what we'll do is we'll do 1 by, we pre-multiply by 1 by G2 here, and this is R. So now this is about the algebra of block diagrams and some rules on how you can simplify block diagrams. Now what we'll do is we'll do an example. So let us consider this particular block diagram. So this is the block diagram which we want to simplify and find y of s by r of s. So here we have here G1, G2, G3, G4, G5 and G6, and we want to find y by r. So now we have this block diagram, and as we discussed we want to simplify it by y by r, right? So what we'll do, we'll first consider one aspect. So we'll focus on simplifying only this portion. So if we simplify this portion, what we'll get is G1, that is whatever is then the forward path, divided by 1 minus, since there is a positive feedback, it will be minus the forward path and the feedback path. Based on this we get So we have simplified this part marked in the red color here. Now we'll focus on to the next one, is using the rules of algebra we just discussed. Is we'll move this pickup point from here to here. And when we do that, this particular part, we can erase this particular path here to get G6 by G2. So what we are doing, we had G6 in the forward path already, and since we are moving the point, we are just going to divide it by G2, and we get this particular expression. Now we can consider simplifying this portion. So what will this give us? It will give us one particular transfer function G5 plus G6 by G2, because this is just summation. Similarly, then what we can do, we can consider this negative feedback, simplifying this negative feedback portion. So the equivalent transfer function between from R to here, this particular point, will get is G1 G2 1 minus G1 G3. So we are simplifying here. So this will be the forward path divided by 1 plus because we have negative feedback, G1 G2 1 minus G1 G3, and the whole thing will be multiplied by the transfer function in the feedback path G4. And once we get that, if we want to find the transfer function between y and r, we just multiply these two parts. So that will be, so we can get y by r as basically G1 G2 1 minus G1 G3 1 plus G1 G2 G4 1 minus G1 into G3. So we have taken this particular part, and now we multiply it by G5 plus G6 divided by G2. So we just multiply these two parts to get our transfer function y by r. So we have so far studied transfer functions, DC gain, and block diagrams. Now at the start we had discussed a transfer function can be expressed as Bs by As. The roots of this are the zeros, and the roots here are called the poles. So what we are going to do is now try to understand what is the effect of poles and zeros. So first we will start with understanding the effect of poles. So let us consider an example. H of s, basically 2s. This is a transfer function of a system. So now for this transfer function, I want to find its corresponding impulse response, that is its time domain representation. which is I'll denote as h of t. This h of t is a very important characteristic of the system. And so how we go about that is, as we have discussed in the last class, we go to find the inverse Laplace transform of this h of s. So we can express this as, these are the two parts, this is minus 1. So we can break down this transfer function using partial fractions. So we have one root at s plus 1, other s plus 2, and we get this. So we can look at the Laplace transform tables and we can get h of t is basically, for t greater than or equal to 0, you will find it's minus plus e to the power. This basically stems from the fact that if it is 1 by s plus a, the inverse will be e to the power minus at, and for t less than 0 it's 0. So what you will see here is that if we are given, we can express it in this form where the poles are real, then the corresponding time domain function will just be an exponential function. And if there are multiple real poles, you will find that we just find a contribution using these partial fractions, and then we take the from the table we take the inverse Laplace transform, and based on that then we just sum it up to get our impulse response h of t. Now this is in the case when there are real poles. Let us consider a case h of s where we have complex conjugate parts. So let us consider a simple spring mass damper system scenario where omega is the natural frequency and this zeta is the damping. So this is h of s for that case, and let us express sigma as zeta omega n, and omega d, that is the damped natural frequency, is given by this expression in terms of the damping ratio and the natural frequency. So if we have, now let us consider the denominator because we are interested in the poles. So we can express this as s square plus 2 zeta omega n s plus square omega n square plus omega n square minus. So here what we are trying to do, we are trying to complete the square similar to what we did in the last class to find the inverse Laplace transform of a function, and based on that we get s plus 2 square plus omega n square minus square omega n square. So this particular part will be basically omega d square from this particular relationship. So we can express this as s plus sigma square based on this particular definition and omega d square. So now if we consider h of s and we look at the table, we find that h of t will be basically omega n by 1 minus zeta square into e to the power negative zeta omega n t sine omega d t. Now let us say we want to understand, this is the impulse response, but where are these particular poles located? So we go back to this particular part here, and since there are now complex conjugate poles, so basically in S plane, this is the real axis, imaginary axis. So complex conjugate poles always occur in pairs. So the root, the poles basically will be the poles here will be, the real part will be sigma, the imaginary part will be omega t, and the magnitude of this will be basically, so this is in Cartesian coordinates. Now we want to do that in the polar coordinates. We look at sigma square plus omega t square, and this will be equal to omega n square. In the polar form, the magnitude is omega n, and this angle is basically sine inverse of theta. So if we are given these particular set of parameters, we can locate what is the pole location in the S plane. So now we have studied what happens when there is real part and what happens in the case when there are complex conjugate poles. So now let us consider the S plane. So here we have the real and the imaginary part. So say there is a basically pole, and poles are basically denoted by this cross symbol and zeros are denoted by this O symbol. So let us consider that there is a pole here at origin. So basically it will be of the form 1 by S. So so we know that 1 by S corresponds to a step input. So basically the the response of this particular, the impulse response, will look something of this form. Now let us consider that we move along the real axis. So let us consider pole here. So in this case, as we have discussed earlier, it will be of the form 1 by S plus A, and that will correspond to e to the power minus at. So we will have something of this form. Now if you move on to the positive side, what you will see is this coefficient here will be positive. So you will have, so it will keep on exponentially growing. So since this is exponentially decaying, after certain time it will when the real part is of the pole is less than 0, it will exponentially decay, and this will represent a stable system. Whereas if it keeps on growing, it will grow unbounded and represents an unstable system. Now if we look along the imaginary axis, along this part on the imaginary axis, as you would have seen here that it depends on the function e, there is some e to the power exponential function and you will have sine, but in case, so there will be, in this case there will be complex conjugate parts, one corresponding here, and we will have to look at this case. In this case, then as we have seen, if they are on the imaginary axis, this sigma is 0. So, basically the exponential part is 0. So, what we are just left with is a sine wave of constant amplitude, and the frequency will vary depending on where we are in the imaginary axis. Now, let us look at the other case when we are here. So, when we are here, there will be, as we have seen here, an exponential part as well as sinusoidal part. So, the response will be, first you will have an exponential part which will determine your amplitude, and inside that you will have a sine wave. The frequency will depend on this omega d, and the exponential part will be determined by zeta omega. Now, if we are on this side, basically what you will see is you will see a similar behavior, but this exponential part, as in this case, will keep on growing and looks something like this. So, this will produce an unbounded condition. So, this region basically represents unstable region. So, if you have poles in this region, that is the right half plane, it is unstable, whereas here you get stable system if your poles are here. So, here we have seen that this if we are in the right half plane, it is an unstable case, whereas if we are in the left half plane, this is a stable case, and if we are on the imaginary axis, since the response will continue to oscillate, it is called marginally stable case. Now, that is all about the effect of poles on how they determine, one is the stability, and the nature, the second is the nature of the response, as you see, whether it is oscillating or exponential or a combination of both. The next part is understanding the effect of the zeros. So, towards doing that, you will see that zeros affect the contribution of terms and the transients. So, what I mean by that is we will look at a simple example. So, let us say h1 of s is 2 divided by s plus 1, s plus 2. Let us consider this particular transfer function. So, this is basically, if I do the partial fractions, I will get 2 by s plus 1 minus 2 divided by s plus 2. So, if we take h1 of t, this is 2 e to the power minus t to the power minus 2t. Now, let us consider an alternate transfer function. So, here in the first case h1 of s, there was no 0, there were only two poles at minus 1 and minus 2. Now, I will keep the poles at the same location, but add n 0. Now, since I am adding 0 here at minus 1.1, the DC gain will change. So, to maintain the same DC gain, I will divide this by 1.1, that is the location of the 0, and then I can express this as 0.18 using partial fractions. So, I get h2 of t is 0.18 e to the power minus t plus 1.64 e to the power minus 2t, right. So, now let us compare these two particular responses. So, the exponential part here remains the same, and that is true because the poles are same. But if you now look at what happens to the coefficients, the contribution of the coefficients is changed. So, if we neglect the negative sign, what you see is here this is more or less they have the same same magnitude, right. Whereas here the magnitude of this particular part is more than the magnitude of this. So, the pole at minus 2 plays a more important role in the response of this transfer function at compared to the pole at minus 1. Although the DC gains are the same in both cases. This is because this pole, this 0 we have inserted now here minus at minus 1.1 is more closer to the pole at minus 1 as compared to the pole at minus 2. So, why this happens is we look at how we got these coefficients. So, these coefficients are basically, say I want to find coefficient for a pole P1, then that C1 will be S minus P1. I will multiply it by my, say, the transfer function, which in this case could be H1 of S or H2 of S, and this S minus P1 into F of S, and I will evaluate this at P1. So, if there is a pole which is basically closer, if there is a 0 which is closer to S is equal to P1, then C1 will be smaller. So, to get a better, say, now in this case we had a 0 which is close to the pole at minus 1. Let us consider an alternate example, a third transfer function, which is basically as a 0 closer to the pole at minus 2. We will maintain the same DC gain. So, in this case what you will get is 1.05 divided by S plus 1 minus 0.1 divided by S plus 2, and your response will be 1.05 e to the power minus t minus 0.1 e to the power minus 2t. So, here you see the contribution of the pole at minus 1 is greater as compared to the pole at minus 2. So, this is the effect of 0 on how it changes these individual contributions and hence the transients, and this will basically be determined, these coefficients are determined by the relative location of the poles and the zeros, whereas poles determine fundamentally how the response will look like, whether it is sinusoidal or whether it is exponential or a combination of the two, as well as the stability of the system. So, with that we will conclude today's lecture, where we have discussed transfer functions, DC gain, block diagram and algebra, and the effect of poles and zeros on the response of the system. Thank you.
Understanding oneself, understanding others, understanding society at large, understanding the nature, these are all driven by basic human curiosity. We would all love to understand why things happen, what happens, what is the final outcome, why certain things fail. These are all exercises that we perform in various domains of knowledge. Therefore, knowledge in various domains, you would realize they are actually social artifacts. They have to be rooted into historical perspective, they have to be culturally salient, and there would be socio-political reasons behind this. Whether you talk with respect to engineering sciences, whether you talk with respect to physical sciences, biological sciences, social sciences, that is the reason why humanities and social sciences should be understood by all of us. The knowledge that is segregated, that is divided with respect to areas, specializations, all of them needs to be understood in its context. And what provides the context? It is the social reality. How do you correlate knowledge in a given domain with the cultural reality, with the social reality, with the socio-political compulsions? Okay, how do you understand the law of nature, okay, in its totality? And for doing that, you require the understanding of humanities and social sciences. Say for instance, if you are trying to understand the effect of a particular bacteria, a virus, any microbe, how it affects behavior, how it affects the organism, human being, you start looking at it from a pure biological point of view. If you are trying to look at a particular type of a wavelength, say for example, you are emphasizing on the understanding of the effect of radiation on human life, you are looking at things from a physical point of view. You are looking at the corresponding changes inside the body, you are looking at the physiological side of the understanding of the information. You are trying to understand why, despite knowing the risk that is inbuilt in the process, why still human beings engage into it. You are looking at it from a pure behavioral point of view. Why society at large admire things which has full of risk. You are trying to understand things from a pure sociological point of view. Why people use particular set of words to explain those experiences. You are trying to understand things from the linguistic point of view. So, there are a whole lot of things, and then finally, you try to combine all of them to say that what are the guiding principles in life. Then you say you are looking at life, you are looking at humanity from a pure philosophical point of view. And this is what social sciences courses provide you. They provide the context to you in which you would be finally positioning the understanding of the knowledge in any given domain. It could be engineering, it could be sciences, it could be medical sciences, it could be social sciences stuff, it could be humanities stuff. So, contextualizing the knowledge is what humanities social science courses help you obtain.